Hello, today I'm going to be talking about the Edmonds-Karp algorithm. It's a Max-Flow algorithm, which is an extension of a Ford-Fulkerson algorithm, which also works on Max-Flows, and these use something called flow networks. And flow network is an extension of a directed graph, which is shown here. A directed graph is a set of nodes or vertices connected by directed edges. These arrows represent these directed edges. And nodes and vertices are two interchangeable terms. I'll be using them both in this video, so don't worry if you hear them both, they mean exactly the same thing. These labels represent the capacity. Now, capacity is the amount that can travel down an edge, and the flow is the amount that is currently traveling down an edge. Here, source, that's highlighted in green, that's a flow producer, and this is a sink in blue, which is the flow consumer. And highlighted here is a path. It's a discrete sequence of nodes and edges connecting two vertices in the network. And in this algorithm, the two vertices you want to connect are the source and the sink. It's a kind of analogous to like a piping system. For example, say like the capacity is the amount of water that can flow down a pipe in the system, and the flow is the amount that is flowing through them. And much like a piping system, you need an entry and an exit, a source and a sink. Otherwise, there would be no flow going through. This here is a cut. It's a bit abstract, but what it does, it forms a pair of disjoint subsets of G, where G is the graph, one containing the source and one the sink. And what it does is it separates a network such that there are no paths from S to T. And cuts have value, and the value of the cut is a sum of the edges going across from the source side to the sink side. That's the sum of those, and that's the max flow. S in this case is a source and T is a sink. I'll be using that a lot in the future. And there's also something called legal flow. Legal flow is what's needed for the flow algorithm to run and not mess up, essentially. And the first one is called a capacity constraint. This is all set notation. It's a bit scary, but it's actually quite simple, really. It's just a shorthand. It says, for all U and V within E, the flow from U to V is less than or equal to the capacity from U to V, which is translated here. The flow along an edge cannot exceed the capacity, which makes sense given the analogy that we just used. Skew symmetry. For all U and V within E, the flow from U to V must be equal to the negative flow from V to U, which the net flow from U to V must be the opposite of the net flow from V to U, which again makes sense. As if you imagine another analogy, so I have two cakes and I give you two cakes. The flow of cakes from me to you is going to be 2 because you've gained 2 cakes, right? That's where the flow, that's the net flow. But if you look at it from the opposite way, the flow from you to me of cakes is going to be negative 2 because I'm losing cakes. Next, we have something called flow conservation. For all U within V, where U is not the source or the sink, then the sum of the flow from U to W has got to be equal to 0. So the net flow to a node is 0 except for the source, which produces, and the sink, which consumes. Which makes sense if you think about the pipe analogy again. Here you've got the value of F, the value of the flow, and it says that the sum of the flow from S to U is equal to the sum of the flow from V to T, which means the sum of the flow leaving the source must equal to the sum of the flow entering the sink, which again, the piping system, you can't have more water coming from nowhere, and you can't have water just leaving. It's always quite a closed system. So here they are in a nice little slide, and these are the 4 properties. So here you go, you've got some pseudocode for the Edmonds-Karp algorithm. And the important thing to note is in here there's something called the breadth first search. I'll call that BFS from now on. This is what distinguishes the Edmonds-Karp algorithm from the Ford-Fulkerson. And the BFS, and this is all computational implementation of the algorithm obviously, so it may be a bit tricky to understand, but in essence the BFS is a tree searching algorithm. Your inputs C, E, S, T and F. C is a capacity matrix inputted in the previous algorithm. It's kind of a representation of all the edge capacity, and E is a set of neighbours. F is an array of legal max flow, S and T we've seen before. MT is the capacity of the path found, and the value in the square brackets is the last node in the path, so in this case T being the sink, it's the maximum flow to the sink from the source, obviously. And P is a parent table which contains the nodes in order of their addition to the path. So you initialize this array, you set all the values to -1, which is completely arbitrary, it can be anything, it just shows you've checked them. You mark that you've checked the source, you define this capacity array, you set it equal to infinity, which is essentially saying that there's not available amount of capacity at MS because there's not been any flow yet, you're still at the source. You define a queue, which is essentially a stack, you pop S onto the queue because that's what you're going to be checking now. So while the queue size is greater than 0, you put U equal to what you pop off the stack, in this case it'll be S, and you set up a loop that checks all the neighbours of this node. Then what it says is if there is available capacity and the adjacent vertex hasn't been checked, that's this node that you're checking now. Bear in mind that you're still looking at the source node, in this case U. You add U to the path array, set the capacity value to the minimum of the capacity of the path up to the node u and the available flow between u and b, which makes sense because you want the minimum value, and otherwise you'll be passing more flow through these pipes than they can manage. Then if the vertex isn't being checked, if the vertex being checked isn't the sink, you add v to the cube. And if it is, you've found the sink, and you return the capacity matrix, and the parent table as a path has been found. Otherwise you return 0, which is kind of an error message. Here we've got a capacity matrix, a set of neighbours, a source and a sink. Excuse me. An output is the maximum flow and a legal flow table or an array. So you initialize both of those, and this loop goes through finding paths and using that error message to break out. If not, it sums maximum flow value and sets this variable to the sink value. And while v is not equal to s, so that allows this v equals t thing allows you to enter this loop. It loops when v is not equal to s, the source, sets a variable u to the value in the parent table of v, and computes the flow, and then moves on. So if you want to see this implemented, here we go. This is a very simple explanation. You can see you've got 0 over 30, that's a pairing, that's flow over capacity. And underneath you've got GF, which is a residual graph. And this is another kind of abstract concept, but it shows additional possible flow in a graph. And so if a path from S to T exists in GF, flow can be added to this network. So if we start with this path has been found using the BFS. We go through it, you can see that the maximum flow addable is 20 if you look at the BC edge. If you look at the residual graph, you'll see that the flow that we've put through is kind of being put through the opposite way in this graph, and what that does is it shows the available capacity. And so if you look at the BC edge now, you see there's no capacity going forward, which basically means you can't put any more flow through that edge. So you do it again for a different path that's been generated, and you end up with another residual graph. If you look at it, you can't really get through it because obviously from A to B there's no more capacity. Same with B to C, D to E, and E to F. So you're done. You've got your residual graph. Now this is where the cuts come into it. The max flow min cut theorem is written there for the network. The value of the max flow is equal to the minimum cut. So what you've got to do, find a minimum cut. You make many cuts. The value of this one is 30 if you sum the edges. Same with this one. So the value, the max flow through this graph is going to be 30. It's quite simple, eh? Also, you've got to talk about the complexity. And the complexity of this algorithm is VE squared. And this comes from the Fulk-Fulkerson complexity of OBEF, F being the max flow value, and the BFS complexity, which is of order BE. You might be wondering, where does that F go? The F is there to mitigate the non-termination of the Fulk-Fulkerson algorithm, but the Edmonds-Karp algorithm will always terminate. That's how you can get rid of that F, and you'll end up with VE squared. Alright, thank you. Hope this helps.